Welcome to a lesson with Dr. Powell. Let's look at an example of finding two different linear combinations of a set of vectors that equals a particular vector that we just select. So let's just select this one, and let's try to find two different linear combinations of a set of three vectors over here that equal it. Now, we can find two different linear combinations where these guys are different if the set of vectors is linearly dependent. Now we know that this set of vectors is linearly dependent in particular because there are three vectors in it. Now in R2, which is where these vectors live, we know that the dimension is 2. The dimension is the number of vectors there are in a minimal spanning set. And if you have a set of vectors that's linearly independent, the number of vectors has to be less than or equal to the size of a minimal spanning set. Because a set of linearly independent vectors is a minimal spanning set for its own span. Anyways, so basically we know just because this is 3 and the dimension of R2 is 2, that this has to be linearly dependent just by a counting idea. Okay, so we know it's dependent, so we know it's going to work. All right, so let's go for it. We have an A times this vector plus B times that vector plus C times that vector. Let's try to find an A, B, and C. Now to do so, we simply multiply the A to these components, B to those components, C to those components, and we add. And we end up getting this equality right here, a system of two equations and these three unknowns. Now, in order to find this, we could just try different things. For instance, we just need to find two different options. What if we just set C equal to be 0? Now, if C is 0, then A is forced to be -1. And then since A is -1, that would force B to be +2 right there. Hey, we just found one. That works. That's a possible solution right there. Now, another way of doing this, we could say A is equal to 0. Let's just set A is equal to 0 and see what that forces B and C to do. Now, if A is 0, that would force C right here to be, so 5C would be -1, so C would be -1/5. Now, if C is -1/5, then this would be -2/5, and A is 0, which would force B to be 7/5. And see if I did that right, because, okay, so yeah, so if we have is so 7/5 must be 1, right? Okay, so that looks good. And then A is 0, and yep, let's see, and that's equal to -1. Looks good. Okay, so we have two different options right here, and we could get it because these vectors right here were linearly dependent. Now, if they're linearly dependent, then the function that's defined that goes from R2 to R2, the additive function that's defined by sending, like, I'll just write it this way, AB is sent to this tuple right here. It's an additive function. So what we were just computing is we were looking at two elements in the same fiber, the fiber over this. Now, if the function is not injective, then that means that there is a fiber that has more than one element in it. Now, the nice thing about these additive functions here is that all the fibers are shifts of each other, so every single fiber is going to look this kind of behave the same type of way. So that means that if it's not injective, every fiber will have more than one element in it, and so we were able to do that right here. Equivalently, for linearly independence means that if we construct such a function in such a way that it would be injective, and just stating it's non-injective guarantees that we have two of these guys. Thanks for watching.